Hello, esteemed friends and colleagues. In this video, I would like to demonstrate and introduce a system I've created which allows the design of 3D print jobs to be done in KiCad without the need for a slicer. Let me describe the end-to-end workflow starting with the KiCad design. The critical idea is the meta component or meta footprint in the KiCad design. These meta footprints are used to create a Lisp language syntax structure where rectangles and points in the two-dimensional space are first-class citizens, just like integers and strings. To understand the structure, see the top footprint. It has the name makeStack, which is a function corresponding to a Lisp function. The function takes two arguments, number of layers and the layers. The first argument is the string of text 8. The arguments are identified by lines from the origin. The order of arguments is determined by the distance to the origin. Now notice the mapChar and partial functions. The first argument to these functions are quoted strings referencing other functions. In the function call to partial, another argument is supplied, which is a via in KiCad, in other words, an xy coordinate. Towards the right, there is a list of two rectangles. Here we can see how points and rectangles are first-class citizens, just like strings. When the design is finished, the next step is to convert the KiCad PCB design into an S expression that can be evaluated by a Lisp interpreter. For this, I have a function called getExpressionTree, which takes the PCB file as argument. You can see that it will output the S expression representing the KiCad design. The next step is to evaluate the S expression representing the design. Here I've chosen to use Emacs as the Lisp environment. Notice on line 3 that the expression tree is loaded, and the expression setQ job output, render job from stack, is where all the heavy lifting is really done. Finally, the rendered GCode is saved to a file where it can then be sent to the printer for printing. Here we can see the rendered GCode. The GCode starts with the preamble, which initializes the printer. Then there are the layers. A layer consists of shapes. A shape is a contiguous sequence of extruded line segments. Once a shape is finished, the filament is retracted and the head is moved to the start of the next shape. When all the shapes have been printed, the next layer begins by moving the z-axis. Let me point out a few more things. Notice at the start of each layer, there are programmatically generated comments to allow for human-readable inspection and sanity checking. Notice the E parameter to the G0 codes. The extrusion length is calculated by the Lisp framework based on the line segment length and the extruder to filament scale factor. Also note that the use of G0 and G1 codes is done with the intention that G0 codes will imply an extrusion, whereas G1 codes imply the moving of the print head and other runtime configuration. The preamble is specified by a Lisp file, in this case called default settings 1.0 mm. This file defines settings specific to the parameters of the printer. It is all basically self-explanatory, but suffice to say that the parameterization is largely targeting the nozzle diameter and the filament material. The last thing to point out in this end-to-end demo is how I send the G-code to the printer. My printer is connected to a remote host running a Clipper, Moonraker, and Mainsail stack. Controlling the printer host from my development host is done with a set of shell scripts, which are very simple, just preparing HTTP requests to the Moonraker server. You can also see a taste of how I maintain these scripts by parameterizing the printer hostname and making these scripts available in my shell path environment variable. So that concludes the demonstration of the end-to-end happy path. Now I'll share a couple cool features that I've added here. Notice the job description specifies the render layer to SVG in temp file, giving a couple layers. And what this does is it can take the definition of a layer and instead of rendering it to G-code, it will render it as an SVG path. This is useful for sanity checking your designs before you waste any time and material on a bad, invalid print job. So here's a feature that I think is really cool. In KiCad, I am able to press A to add a footprint, and we can see all of these definitions of meta footprints I can select with descriptions and lists of arguments. These footprints are actually automatically generated based on the Lisp functions that they correspond to. And here we can see the KiCad footprint syntax defining each one. In KiCad, I simply configured the path to where it should search for footprints to that location. That worked out very nicely. Now, to conclude this video, if you are still with me here, I imagine you are curious to see more detail. But rather than to show you any of the internals or source code, which is just a pile of source code, I would like to share with you the two ideas that are really the true essence that makes this solution possible. And that is, one, the use of Lisp and its quoting and macro abilities, and second, the fact that KiCad represents its data in the S expression format. The use of quotes in Lisp is what allows rectangles and vias to be first-class citizens, just like strings. The quote allows the rectangle and the via to be a literal value that is also a list. This is important because otherwise, without the quote, a list would be interpreted as a function call. Quotes also have another important role, which is that when functional operations like mapcar and partial application are used, they need to reference a function itself, or a lambda describing an anonymous function. Here, because of the simple and easy syntax of quoting a string by prepending it with the single quote character, this allows for a convenient shorthand to refer to a function by its name instead of going through the explicit long-winded definition of a lambda. Finally, I would like to say that what I've shown you would not be possible without KiCad. And this is precisely because KiCad stores its data in plain text and in the S expression format. Because of this, the need for a parsing or conversion between the native format of the CAD data and the meta representation of structure around the CAD data goes away for free. Otherwise, for example with Eagle, it would be simply annoying, if not impossible. Moreover, the fact that KiCad uses the expression format means that the meta footprints also being represented in the S expression format naturally fits into place. As far as I understand, KiCad is the only suitable platform for this system. I should note that I do believe that this would have been possible in Inkscape because it uses natively the SVG format, which is basically XML and is effectively the same thing as an S expression, being a nested tree structure. However, if you didn't catch this already, I actually use KiCad to design circuit boards, and I think there's a lot of power and potential with the idea of integrating two-dimensional circuit board layout with three-dimensional 3D prints related to those circuit boards, particularly in the design of enclosures, and as I showed you a little bit of, for things like manufacturing jigs and drill templates. Thank you very much for watching this video. My name is Steve Anderson at the Pizza Beer headquarters. I wish you the best of luck and happy hacking.